Hi class, welcome to lesson 12. This is the first lesson in unit 2. This lesson was done in class via stations, but in case you missed the lesson or you're having trouble and you want review, here's a lesson for you. In this lesson, you will learn to identify the properties that distinguish the three states of matter: solid, liquid, and gas. There are additional states of matter, but in Regents chemistry, we're going to focus on these three. Construct a particle diagram for solids, liquids, and gases, and determine the direction of heat flow.
Chemistry is the study of matter and its changes. Energy is what changes matter. There are two types of energy when dealing with matter. There is kinetic energy and there is potential energy. Recall from the previous unit that kinetic energy, the energy of motion, is related to temperature. Recall that the average kinetic energy exactly equals the Kelvin temperature. Remember, when the Kelvin temperature is 0, there is no molecular motion. It is always true that when kinetic energy is changing, so is the temperature. Potential energy is considered stored energy, but in this class, we can better understand potential energy as phase energy. Potential energy is related to the position of the particles. You already should know that when you change phase, you change the position of the particles. Here, the solid particles are tightly packed together. But as I change the phase to a liquid, I spread the particles out. I change their position. A change in phase or a phase change is always a change in potential energy. Chemical changes also experience potential energy, but those are a little bit more complicated. Let's look at a picture here. Here we have a chemical change. Here we have a bond being formed. This again is a change in potential energy because notice that the atoms of hydrogen are coming together. They are coming closer together. So their positions are less far apart. So here is a change in potential energy.
A minute to pause the video, as this is all of the important information you're going to have to know about solids, liquids, and gases, in addition to their particle diagrams. Most of this information should be reviewed from elementary school. The two new ideas that you might have here are the ideas of the intermolecular force. An intermolecular force is the force that holds particles next to one another. It is not a bond, it's just an attractive force that holds one particle next to another. Solids have really strong intermolecular forces. That's why they have both definite shape and definite volume. The particles that hold them together are strong enough so that they can maintain their shape regardless of the container they're placed in. Versus gases essentially have no intermolecular forces. Gases immediately spread out of their container. Entropy is another word for randomness or disorder. Solids are very organized. Their particles are said to be in a fixed, vibrating crystalline structure, while gases are in constant random straight line motion. The randomness indicates that gases have very high entropy.
You can see a description of the three states of matter and the phase change that occurs when you change from one state to another. Many of these are likely to be reviewed. I am pretty sure you already are aware of what melting and freezing, vaporization or boiling, and condensation are. But the two new phase changes that you might not be familiar with, but are very important, are sublimation, which occurs when a solid turns straight into a gas. This happens with dry ice or carbon dioxide. It also happens with iodine. It is very important that you know what sublimation is, or the verb is to sublime. So carbon dioxide and iodine are two substances that readily sublime at STP. When we change from one phase to another, we also change the entropy, or the measure of disorder. So when we look at solid, liquid, and gas, we see solid has the most order because it has a definite shape and a definite volume. And gas has the least order because it has no definite shape and no definite volume. When answering questions, you can always replace the word entropy with disorder.
One important idea for you to understand is that all particles are in motion. Solid particles vibrate in fixed positions as they maintain a definite shape and a definite volume. Solid formulas are ended with the symbol S in parentheses. Liquids have slightly weaker intermolecular forces. Liquids have definite volume, meaning if you put 1 cup of a liquid in any container, you'll still always have 1 cup of a liquid. But they have an indefinite shape. They always take the shape of their containers. Liquids are in constant motion, which allow them to flow. The symbol L symbolizes liquid. Gases have the most kinetic energy. They are in constant random straight line motion, and they have no intermolecular forces holding them together. That's why gases have no definite volume. They always completely fill their container. Watch as this piston compresses on the gases. Regardless of where the piston is, the gases always completely fill the space they are allotted. Gases have no definite shape. They always, again, uniformly or completely fill their containers. Gases are compressible because they have so much space between their particles. The symbol G is used to symbolize a gas. One important idea to recognize is that since heat is a form of energy that comes about from particle motion, and all particles, including solids, are in motion, heat always travels from hot to not. So if you have a substance that is hotter than the surrounding temperature, then heat will flow out into the surroundings. Or like in ice cream, the heat from the surroundings will flow in to the cooler substance. Recall that the average kinetic energy is always the same as the temperature. So by now, you should be able to identify the states of matter, construct a particle diagram for solids, liquids, and gases, and describe the direction of heat flow. The last thing we want to look at here is entropy or randomness. So in the universe, entropy is always increasing. So if I drop a box of crayons on the floor, it's always going to become scattered and it's not going to drop and arrange the crayons in color order. Another example of entropy is your room. One day you clean your room and the next day it's a mess. Gaseous mixtures are another really good example of how entropy is always increasing. So if you have gaseous mixtures separated and you open up the valve, the gaseous mixture will spread out evenly, always. Never will the gaseous mixture that is spread out condense to one side. This is another example how entropy or randomness of the universe is always increasing. There are 5 major ways to increase entropy. The first way is to increase temperature. The higher the temperature, the more entropy, because the particles are moving faster. The other way to increase entropy is to change the state of matter. Gases have the most entropy, then aqueous substances, then liquids, and then solids. So when we change from a gaseous substance to an aqueous substance, entropy decreases. But if we change from a solid substance to an aqueous substance, entropy increases. Liquid to gas is an increase in entropy because it's becoming more random. Same as solid to liquid. The other ways we can increase entropy are by making a mixture versus a pure substance. Mixtures always have more entropy than pure substances like elements or compounds. The type of matter, elements always have more entropy when they're free than when they're bound in a compound. And finally, since gases have the most entropy, if we have a reaction that creates more gas than we started with, the entropy will always increase. So in this chemical reaction here, you can see that I begin with 2 carbon monoxide and 1 oxygen to produce 2 carbon dioxides. So I start off with 3 gases, 2 carbon monoxide and 1 oxygen. That's 3 gases, but I only end up with 2 gaseous particles of carbon dioxide. So in this case, my entropy is decreasing because I have less gas. So by now, you should be able to describe a change in entropy.
The last thing we'll examine today is the difference between endothermic reactions and exothermic reactions. We will visit this concept throughout the entire year. Take a moment to pause the video so you can get these notes down. Endothermic reactions absorb energy. During phase changes, that can be used to spread the particles further apart and increase entropy. During chemical changes, endothermic reactions are used to break bonds. Breaking bonds can spread particles further apart. Notice that in endothermic reactions, heat can be written as kilojoules or simply as the word heat, but in a chemical reaction, it will always appear on the reactant side, and the delta H, or the symbol for heat, will always be a positive sign. Exothermic reactions always release heat. During phase changes, this release allows the particles to move closer. During a chemical change, the release of energy allows for the making of bonds. This is why most substances are found bonded together, because together, bonded, they can have lower energy. They can release the excess energy. Notice how exothermic reactions have the heat term on the product side, or the delta H is negative. You should not memorize if a reaction is endothermic or exothermic, but instead you should use reference table I. It is hard to determine if a reaction will be endothermic or exothermic because in most reactions, bonds are both made and broken. Notice here for this reaction for the formation of hydrochloric acid, we have to break bonds on the reactant side before we can make bonds on the product side. So again, we can look at reference table I to see if this formation is endothermic or exothermic.
So this marks a conclusion of lesson 12, heat and entropy. Make sure you've taken good notes. You complete your homework in Google Classroom. You make sure you put your reference table and calculator back in your backpack, and I'll see you in class soon.